Thank you very much. Let me first thank the organizers for the invitation, which I must say came as a surprise because I'm not an expert in quadratic forms. I'm definitely not an expert in linear algebraic groups. And probably I'm not an expert in beyond. So, or perhaps a part of beyond, if you allow me to say so. And but anyway, I came to work a little bit with algebraic groups while studying gradients on simple algebras, and I arrived to study gradients of simple algebras because of some work on octonions. So I arrived to this field of linear algebraic groups through these gradients, and I want to give you a view of the things we have been doing and the things that are known about the classification of gradients on simple algebras. Okay, so to begin with, gradients reflect symmetries on the algebras, and sometimes they help us to study these algebras, to uncover the structure. And gradients on Lie algebras have been studied for years and years from the very beginning. I mean, the Killing-Cartan classification of the simple Lie algebras over the complex numbers starts with a suitable subalgebra, Cartan subalgebra, and the root space decomposition, and this is a gradient, and the combinatorics of this gradient that appears is important in the classification, the different possibilities for the spaces. But gradients by smaller groups like the integers modulo 2 have been important too in dealing with symmetric spaces in geometry, or when one considers the affine Kac-Moody Lie algebras, one starts with a gradient by finite cyclic group on a simple Lie algebra and considers the corresponding loop algebra as a center, as a derivation on top, and gets the Kac-Moody Lie algebras. And also, when dealing with Jordan algebras attached to any Jordan algebra, there is the famous Titz-Cantor-Kecher construction that gives you a Lie algebra graded by the integers with only 3 non-zero homogeneous components, the 0, 1, and -1 parts of the gradient. And we can extend this to more general Jordan systems like Jordan triple systems or Jordan pairs, and still keep these 3 gradients on Lie algebras. When dealing with structural algebras, one gets grading 5 gradients on Lie algebras. And dealing with more general Jordan systems, one gets gradients by the integers with some depth on Lie algebras. And one can move from Jordan algebras to Lie algebras and back, or Jordan systems in general, to Lie algebras graded by the integers and back to the Jordan systems. But systematic study of gradients, well, first, this is what I want to do the outline. I will give you basic definitions of gradients. Then I will connect gradients with diagonalizable group schemes. And then I will review a little bit what we know about gradients on simple algebras. The results in general are very technical, and I will skip technicalities, just give the ideas which, on the other hand, are quite natural. So, yeah. So this is the outline. And about gradients, as I was telling you, gradients are important and have been important from the very beginning in the study of Lie algebras. But a systematic study began with this paper, Gradients on Lie algebras by Patera and Zassenhaus. And most of the definitions that we use appear in this paper. The idea of Patera and Zassenhaus was to classify the so-called fine gradients on the simple Lie algebras over the complex numbers, finite dimensional simple Lie algebras over the complex numbers. And this was partly achieved later on by Patera and some collaborators. But well, I will talk about this later. But anyway, in this paper, this preliminary paper, several definitions were given, and these are definitions the definition that we use nowadays. So I guess the definition of grading, we don't need to give the definition. Since I will be dealing with gradients on simple Lie algebras, even if we grade Lie algebra, simple Lie algebra by a non-abelian group, the support of the gradient generates an abelian group. So actually, gradings by non-abelian groups on simple Lie algebras are indeed gradings by abelian groups, by a subgroup of the grading group. So there is no restriction assuming abelian groups. So all the groups here will be abelian, and then grading by the group G on algebra, not necessarily a Lie algebra, not necessarily associative algebra. It's just a decomposition as a direct sum of the homogeneous components labeled by the elements of the group, and the multiplication in the algebra behaves nicely with respect to the multiplication of the group. So whenever we multiply homogeneous components of degrees G1 and G2, we end up inside the homogeneous component of degree G1, G2. In general, not all homogeneous components will be different from 0. So we consider the support, which is just the set of labels such that the homogeneous components are different from 0. Okay, so these are part of the definitions and examples. The first one, and perhaps the most important one, the root space decomposition of any semi-simple Lie algebra over the complex numbers. We start with a Cartan subalgebra and then take the eigenspaces by the adjoint action of the Cartan subalgebra. This gives the root system, and this is a grading by a free abelian group of the rank of the semi-simple Lie. And this is well known and has been behind the classification of semi-simple Lie algebras. So this grading will appear constantly, and some gradings will be a mixture of this grading with some other gradings. But let me show you another example of a different kind, not just on Lie algebras, but on associative algebras. These are the gradings produced by Pauli matrices. So assume that we start with n by n matrices, and that our ground field contains a primitive nth root of unity, epsilon. And then we can consider these two matrices, X with the roots of unity, the nth roots of unity on the diagonal in some order, and Y the permutation matrix that permutes cyclically all the basic elements. And then, well, both of these matrices have order n, and they almost commute. So they commute up to the root of unity, up to epsilon. So yx equals epsilon xy. And then essentially we have polynomials in x and y. So we have a basis consisting of monomials with exponents up to n-1, because the order of x and y is n. And this gives a splitting, and this gives a grading, actually, a grading by the integers, two copies of the integers modulo n. And all the homogeneous components are one-dimensional. And even though this algebra is definitely not a division algebra, but all non-zero homogeneous elements are invertible, because x and y are invertible elements, and therefore all these monomials are invertible. So all non-zero homogeneous elements in this gradient are invertible. And then we say that A is a graded division algebra. And then, well, graded division algebras play a key role in studying gradients in associative algebras and on Lie algebras. And see, this gradient induces a gradient on the special linear algebra, and here all the homogeneous components. All the homogeneous components have dimension 1, and the homogeneous component corresponding to the neutral element in the group now is 0. And all the others are total one-dimensional subalgebras of the special linear algebra. So while studying gradings on associative algebras, well, the interesting gradings appear as combinations of sort of Cartan gradings and this kind of Pauli gradings. So sometimes the grading is part of the definition of, or we consider the grading group as part of the definition of the grading, but sometimes the grading group is not the natural one. I will show you an example. And then an invariant of the grading is given by the so-called universal grading group or universal group, which is the group generated by the support and subject to the relations imposed by the multiplication of homogeneous components. So we consider the support of the grading and we impose a condition, a restriction, each time we have that the product of two homogeneous components is different from 0. This is important. And the product of two homogeneous components is contained in a third homogeneous component. So we impose the restrictions in the group G, in the grading group G, but not all of them. And this way, we get an invariant of the grade. And there is a natural one-to-one map from the support to the universal grading group. And then this map induces a natural homomorphism from the universal group to the original grading group. And this is the natural grading group. Given a grading by an abelian group, or even in marginal situations, this is the natural grading group. So let me give you an example, an easy example. Consider the simple Lie algebra of dimension 3, SL2, the special linear algebra of degree 2, and we have the natural basis that consists of the semi-simple element H and the nilpotent elements X and Y. So H acts in a diagonal way, and X and Y are eigenvectors, and the bracket of X and Y is H. And well, this splitting of SL2 is a grading by the integers modulo 3. Yes, because yes, we take H of degree 0 and X of degree 1 and Y of degree 2 in the integers modulo 3. But see, this is not the natural group. Just the way the multiplication behaves, the way the homogeneous components multiply, impose that the degree of H must be the neutral element of the grading group. But the only other restriction that the multiplication of homogeneous components impose is that the degree of X and the degree of Y must be inverses one of the other, or opposite, depending whether we use additive notation or multiplicative notation. So what happens is that the universal group is the integers, is the group generated by the degree of H and the degree of X and the degree of Y. And the only restriction that we impose is that the degree of X times the degree of Y is the neutral element, and the degree of H must be the neutral element. Okay, so the same splitting of SL2 can be given as a grading by many different groups, but the universal group is the natural one. Okay, this is one invariant of the gradings, and this is one of the invariants that was considered by Patera and Zassenhaus. Now, there is, I already told you, sometimes we consider the category of G-graded algebras sometimes, of some variety, and therefore we fix the grading group G. Well, if we are interested in fixing the grading group G, the natural notion of equivalence of gradings is this notion of two gradients being isomorphic if there is an isomorphism of the corresponding algebras that takes the homogeneous component of degree G to the homogeneous component of degree G in the second algebra. However, we may consider the gradients just as splittings, nice splittings of the algebra, and then we get a weaker version, and this is the notion of equivalent gradients. Here, the grading groups may be different, and we say that two gradients are equivalent if, again, if there is an isomorphism of the corresponding algebras, such that homogeneous components are sent to homogeneous components, but the degree may be different, completely different. So this is the notion of equivalence. And sometimes we're interested in classifying gradients up to isomorphism if the grading group is important, and otherwise the natural classification is up to equivalence. And these are the two types. Now, let me show you some groups that are naturally attached to any gradient and become invariants of the gradient. One is the automorphism group, which is the group of auto-equivalence, self-equivalences. So these are the automorphisms of the corresponding algebra that permute the homogeneous components. Another group is the stabilizer group, which is the subgroup of the previous one that fixes the automorphisms that fix each homogeneous component. The quotient of these two groups, well, before the quotient, the diagonal group is as a group of the stabilizer group that acts as a scalar on each homogeneous component. Okay. And the last group is the quotient of the automorphism group modulo the stabilizer group, and this is called the Weil group because, well, for Lie algebras with the root space decomposition, well, if there are no outer automorphism of the algebra, then what we get, if we consider the root space decomposition, is the classical Weil group. Okay, and all these become invariants of any gradient. So all these appear in this paper by Pater and Zassenhaus. And actually, what happens is that any self-equivalence of a gradient permutes the elements of the support, permutes the homogeneous components, and therefore permute the elements of the support. The elements of the support generate the universal group. So any automorphism of the gradient induces an automorphism of the universal grading group with kernel destabilizer. So the Weil group gets embedded into the automorphism group of the universal grading group. In general, the Weil group doesn't embed into the automorphism group of the grading group because the grading group may not be the natural grading group. And so we have to rely on the universal grading group to be able to embed the Weil group there. Okay, these are some of the definitions. And also I need the connection between the diagonal group and the universal group. See, the diagonal group consists of those automorphisms that act as a scalar on each homogeneous component. And then the scalars, since these are automorphisms, the scalars are different from zero, so we get a map from the support into the multiplicative group of the field, and this extends in a natural way to a character of the universal grading group with values in the field. And conversely, so the diagonal group is nothing else but the group of characters with values in the field of the universal. And then what happens is that, well, the characters of an abelian group separates elements of the of the group. So what happens is that over an algebraic process field of characteristic 0, the homogeneous components of any grading by an abelian group, gamma, are nothing else but the eigenspaces relative to the diagonal group of gamma. So that was the idea of Pater and Zassenhaus, that in order to study gradings, one should study suitable abelian subgroups of the group of automorphisms of the algebra, and to study the eigenspaces, the corresponding decomposition into eigenspaces for these abelian diagonalizable subgroups. And finally, about the definitions, given any two gradings on the same algebra, we say that the first gradings are refinement of the second grading if the homogeneous components of the second grading consist of the sum of several of the homogeneous components of the first grading. Okay, so the homogeneous components in the first grading are smaller and contained in the homogeneous components in the second grading. Or in this situation, we also say that gamma prime is a coset of gamma. And then a fine gradient is a gradient that admits no proper refinement. And these are the gradients that were studied by Patera, Zassenhaus, and collaborators. And because these are important, because any other gradient can be obtained as a coarsening of a fine gradient. So in principle, in order to classify gradients, we can classify fine gradients and then take coarsenings of these gradients. And coarsenings can be obtained in a combinatorial way, starting from the universal gradient. But the combinatorics is quite involved, and trying to classify gradients in this way is hopeless, partly because gradients may be coarsenings of different fine gradients, and it's difficult to see when two gradients obtained in different ways are equivalent. But anyway, over an algebraic process field of characteristic 0, the diagonal group of any fine gradient by an abelian group is always a maximal abelian diagonalizable subgroup of the group of automorphisms of the algebra. So it is a quasi-torus of the group of automorphisms.
I have a question. Sorry, yes. I have a question. Why is that clear that you can always find a fine grading if you have a grading? I mean, when you refine, when does it stop? Why does it stop?
If you are able to classify fine gradients, in principle,
but why can you, the remark, why if your grading is not fine, okay, you refine it, but why does it stop at some
yeah.
Why is that a finite process?
I forgot to say, although it was written in the first definition, I'm dealing with finite dimensional algebras. So just by dimension, whenever you refine, you have a finite number of components. The dimension of the components gets lower and lower when you refine, and so it's just because of this. But you are right.
No, okay, thank you.
Yes.
And this map that takes G to G prime, is that required to be a homomorphism?
No, if you are dealing with groups G and G prime. If you are dealing with universal grading groups, then it becomes a homomorphism. So that's why it's important, in order to classify things, to deal with universal grading groups. So in principle, this map that takes the G to the G prime doesn't need to be a group homomorphism unless G and G prime are the universal grading groups. But unless G is the universal grading group of gamma, this is the important thing. Yes.
I see. So, for example, the identity map will, if you use different groups, may not be it's a refinement, but it may not be a homomorphism.
Yes. Okay, so let's move to group schemes, because, well, all these things work nicely over algebraically closed fields of characteristic 0, and that was the idea of Patel and Zassenhaus to classify gradings on the semi-simple, finite dimensional Lie algebras over the complex numbers. That was originally the idea. So the idea was to start with simple. The way to go from simple to semi-simple is tricky, and but has been obtained recently. And but in order to deal with fields of prime characteristic or non-algebraically closed fields in characteristic 0, the study of diagonal maximal abelian diagonalizable subgroups of the automorphism group is not enough, and we must go to automorphism group schemes. Okay, so that's the next point. And well, I guess this definition is not needed here, but just in case, whenever we start with an abelian group G, we have an associated diagonalizable group scheme, and this is the group scheme whose representing Hopf algebra is the group algebra of our abelian group G. Okay, so these are the diagonalizable group schemes, and in case our abelian group G is finally generated, we will call this a quasi-torus. So we'll be dealing with this quasi-torus. So the multiplicative group scheme is a quasi-torus because the representing Hopf algebra is the group algebra of the integers. The same with the group schemes of roots of unity. So you know very well all these things. So we have anti-equivalence of categories between abelian groups and diagonalizable group schemes that restricts to finally generated abelian groups and quasi-tori. And diagonalizable group schemes behave in a very nice way. So subschemes and quotients are again diagonalizable. And quasi-torus, quasi-tori, these are the schemes that will appear, are exactly up to isomorphism, the finite direct products of copies of the multiplicative group scheme and the group schemes of roots of unity. So this is all well known. And what I want to stress is the following. Well, if we have a homomorphism of affine group schemes, well, this is determined by Yoneda's lemma by the generic element of, and the generic element is an element of the second group scheme point with values in the Hopf algebra representing the first group scheme. So we start with the generic element of the first group scheme. So and this corresponds to the we have the Hopf algebra that represents the first group scheme, which is denoted in this way here. And then the homomorphism from this Hopf algebra to itself gives the generic element of this group scheme. You take the image, and then you take what you get is a generic element that determines completely this homomorphism of a affine group scheme. Once you know the image of the generic element, you can get the image of any other element over any with values in any algebra R. Okay. So, oops. So in particular, if we start with a homomorphism from a diagonalizable group scheme into the general linear group scheme of a vector space V, then this generic element is just a linear map over the group algebra of the group G of V. And then we can restrict to just V, which lies inside this element. What we get is the commodule map. So just Yoneda's lemma gives us that, it's quite interesting, that just this generic element determines everything about this homomorphism. When we start with a diagonalizable group scheme, the Hopf algebra representing this group scheme is the group algebra of G. And then the generic element that determines this theta is just an element of GL of V tensor, the Hopf algebra. So, and by restriction gives a map from V into V tensor, the group algebra. And this is the commodule map. And the interesting thing is that this induces a gradient on V by the abelian group G, where the homogeneous components are just the eigenvectors with eigenvalue G. So this is a linear map, but not over a field, but over this Hopf algebra. And then, well, we can consider eigenvectors. And then, well, the elements of the vector space V that are eigenvectors with eigenvalue G for any G in our abelian group G. This is a subspace, and it turns out that this gives you a gradient. So V is the direct sum of these subspaces. But of course, here V is just a vector space. However, if we are dealing with finite dimensional algebras, well, see, any gradient on a vector space comes from a homomorphism from the corresponding diagonalizable group scheme. Well, if this is a gradient as an algebra, what happens is that the corresponding homomorphism from the diagonalizable group scheme is not just a homomorphism into the general linear group, but factors through the group scheme of automorphisms of our algebra A. And then what happens in this situation is that the corresponding commodule map is not just a linear map, but a homomorphism of algebras. And conversely, given any homomorphism, we can consider the corresponding eigenspaces with eigenvalues, the elements of the group, and this gives a gradient by the group G on the algebra. So G gradients, starting with an abelian group, G gradients are given by homomorphisms from the corresponding diagonalizable group scheme into the group scheme of automorphisms of the algebra A. And this is key to study gradients over fields which are not algebraically closed of characteristic zero. We have to forget about the diagonal groups of the gradients and consider these diagonalizable groups. And again, the homogeneous components are just the eigenspaces for the generic automorphism. So once we have one of these homomorphisms, we take the corresponding generic automorphism, which is an element here, a point here, a point over the Hopf algebra representing the first group scheme. And this gives the generic automorphism of A, and you just take the eigenspaces of this generic automorphism. And these eigenspaces give the homogeneous component of the gradient. And this works in both directions. Given the gradient, you take the homomorphism, and in the reverse direction. Okay, so this is what happens moving to general fields, not just algebraically closed fields of characteristic zero. And then if we have two gradients by the same group G on different algebras, well, with the corresponding associated homomorphisms, these are isomorphic, the two gradients are isomorphic, and remember that isomorphic means that homogeneous component of degree G is mapped to homogeneous component to the homogeneous component of degree G, if and only if, well, the corresponding homomorphisms satisfy the natural property for any R in the category of unital commutative associative algebras. I always think of group schemes as functors from the category of unital commutative associative algebras into the category of groups. So this is the natural condition, the conjugation condition. And something similar happens for the problem of equivalence. And well, I will restrict to fine gradients. And for fine gradients, what happens is that the grading is fine if and only if the corresponding diagonal group scheme is a maximal quasi-torus of the automorphism of A. So take the grading, take the universal group gradient, so the natural group. This is a gradient by this universal group. Then it has a corresponding diagonalizable group scheme that corresponds to the universal gradient group, and this is isomorphic to this diagonal group scheme. And this is a maximal quasi-torus. So this works working with the universal gradient group. So fine gradients correspond naturally to the maximal quasi-tori of the group scheme of automorphisms. And two fine gradients are equivalent if and only if the corresponding maximal quasi-tori are conjugate. So this is quite natural. Okay. And so we have to move to group schemes to deal with gradients in general. And one interesting thing about all this is that we have a tool to transfer gradients. So if we have two finite dimensional algebras over a field and we have a homomorphism of the corresponding group schemes, well, any gradient on the first algebra A is given by a homomorphism of group schemes from the corresponding diagonalizable group scheme D of G into the group scheme of automorphism A. Now we can compose with this homomorphism of group scheme and get a gradient in B. In this way, we can transfer gradients from A to B. And when we do this, well, things work in the most natural way. If we have an isomorphism of affine group schemes, then if we have two G gradients on A, these two G gradients are isomorphic if and only if so are the corresponding G gradients on B. And the same, if we have two fine gradients on A, these are equivalent if and only if the corresponding gradients on B are fine and equivalent. Okay. So everything works as it should be. And we can transfer all these groups.
So are you always considering Lie algebras, or are you considering other types of algebras?
No, in principle, all these things about gradients work for not necessarily associative algebras, so non-associative algebras. And the way is that in order to study gradients on Lie algebras, we are going to transfer gradients from other types of algebras. So it's easier to classify associative algebras than to classify Lie algebras, let's see. So in order to classify simple Lie algebras type A over fields of prime characteristic, well, we can transfer the problem to classify. So we have to classify, let's say, twisted forms of the special linear Lie algebra. Well, we can classify twisted forms of the corresponding algebra of matrices, which is associative. Well, not exactly, because the group schemes of automorphisms in type A are not exactly isomorphic, but almost. And then one classifies associative algebras. So with gradients, we have exactly the same situation. Because in the end, we have to classify diagonalizable group subschemes of the group schemes of automorphisms. And this is the way to study gradients on simple Lie algebras. So the clue is to classify gradients on the classical simple Lie algebras over arbitrary fields is to reduce this classification to the associative set, just using this transfer of gradients. So what we have to do is to use classical results on group schemes on gradients. And this is what we do. So for orthogonal and symplectic Lie algebras, well, this appears starting with an associative algebra R with a, well, in order to obtain central simple Lie algebras, we start with a central simple associative algebra and an involution of the first kind. Okay. And then what happens is that whenever we have an associative, central simple associative algebra with an involution of the first kind, we can consider the corresponding group schemes of the group scheme of automorphisms that preserve the involution, commute with the involution. And then whenever we have this involution, we have the Lie algebra, which is obtained as the skews symmetric elements relative to the involution. And this is a Lie algebra. And we have by restriction that any automorphism in the associative setting restricts to an automorphism in the Lie setting. And with a few exceptions, these are isomorphisms. And the exception, well, are these. If the involution is orthogonal, we will assume that the degree is at least 5 and different from 8. And if it is symplectic, we will assume that the degree is at least 4. And the problem with dimension 8, with degree 8, is that the group scheme of automorphism in the Lie algebra setting is larger because of triality in D4. And because of triality, this group scheme of automorphism is larger than this one. And then the classification of gradients is a bit more difficult because of this. But with these exceptions, this is an isomorphism. So in order to classify gradients on our simple Lie algebras, it is enough to classify gradients on the associative set. And for special Lie algebras, something similar happens, but we have to deal with étale quadratic algebras of dimension 2 over our ground field F. Characteristic 2 will be avoided here. We start with a finite dimensional central simple associative algebra over K of degree at least 3, but now with an involution of the second kind. Now, if we take the skew symmetric elements with respect to involution, we have the algebra, but in general, well, it may fail to be simple. So we have, in order to get a simple Lie algebra, we have to take first the derived subalgebra, and then take the quotient with the central part of the derived subalgebra. And this is a simple Lie algebra, and again, with some exception, and in this case, the exception is in characteristic 3 and degree 3. With these exceptions, the natural restriction homomorphism gives an isomorphism between the group scheme of automorphism in the associative setting and the group scheme of automorphism in the Lie algebra setting. And then we can translate gradients in the associative setting to the Lie setting, with problems for D4 because of the triality phenomenon, and some other problems that appear, some exceptions that appear. And but now one has to study gradients in the associative setting, but this is easy. If we start with a graded simple associative algebra with involution, we have two possibilities, that R is not graded simple, and then the involution up to isomorphism is an exchange involution. And otherwise, our finite dimensional algebra is an algebra of endomorphisms of a vector space over a graded division algebra, like this grading by the Pauli matrices of matrices. So this D is not in general a division algebra, but a graded division algebra. And then the involution comes from either Hermitian or skew Hermitian homogeneous form. And then the problem translates into classifying graded division algebras and Hermitian or skew Hermitian forms on vector spaces over graded division algebras. And well, the classification of graded division algebras is even makes sense even over algebraically closed fields. Because over algebraically closed fields, the only finite dimensional division algebra is the field itself, but there are graded division algebras over the field itself, like the examples with the Pauli matrices. And well, over algebraically closed fields. The examples are essentially exhausted combining these Pauli matrices, but over even over the real fields, situation becomes much more important. But anyway, this is the way of classifying things in the Lie setting, just moving to the associative setting and take into account these things. Even for graded division algebras, well, a graded division algebra is graded simple and maybe considered as a graded central simple, but it may fail to be simple or central simple as an algebra. But there is a way to move from graded central simple to central simple ungraded using a twisted loop algebra construction. So we have many tools to deal with these kind of problems that appear in the associative setting. Okay, and this is about the associative setting, and this allows us to transfer things from the associative setting to the Lie setting with group schemes, and we move from the associative classifications to the algebra classification. And see, what do we know? Well, in the first papers, Patera and Sachsenhaus wrote this first paper in 1989, and almost 10 years later, Patera and Pelantova and then some other papers obtain a description of the fine gradings on the simple classical Lie algebras over complex numbers, other than before, because the problem of triality. And it was a description, not a classification, so they prove any maximal quasi-torus of the group of automorphisms is up to conjugation 1 in this list. But there was the possibility of getting some more conjugations in their list. A complete classification, including D4, was obtained in 2010, and D4 was the most difficult case because of the triality. And then over algebraically closed fields with characteristic different from 2, it was Bakhturin and his collaborators, Segal, Seisev, Sestakov, also Koshetov, and I guess I mentioned the main collaborators of Bakhturin, that they dealt with gradings in the associative settings on matrix algebras with or without involution, and transfer the results to the classical simple algebras. Again, they were not able to transfer the results for D4 because of the triality phenomenon. And essentially, at least over algebraically closed fields, one gets a combination of Pauli gradings and some coarsenings of Cartan gradings, but very subtle combinations of these two types of gradings, what one gets. So for algebraically closed fields, already over the real fields, the situation becomes much more involved than just the classification of the graded division algebras becomes much more complicated than over algebraically closed fields. But D4 requires a different treatment, and this was done a few years ago together with Koshetov. Essentially, everything I've done of gradings on Lie algebras has been done with my colleague Misha Koshetov. And also, and this is how I met Koshetov, I put an exception in characteristic 3. And when one studies Lie algebras type A2, simple Lie algebras type A2 in characteristic 3, what happens is that the group scheme of automorphisms, of the split algebra, simple Lie algebra of type A2, is not connected to the group scheme of automorphisms of matrices, but is connected to the group scheme of automorphisms of octonions. So gradings on PSL3 or on twisted force of PSL3 are connected to gradings on octonions, not on matrices. And this is how I met actually Koshetov, because they had a problem with this exception, and I solved the exception using octonions. And then even over the real numbers, gradings have been classified very recently because there are a lot of technicalities, and this has been done quite recently. And also, what about the exceptional cases? Well, for the exceptional cases, we have many open problems. And let's see if you can give me some ideas to deal with some of the problems that we have. For G2, things are relatively easy, because if we start with a simple Lie algebra of type G2, the group scheme is a group of type G2, and this is isomorphic to the group scheme of the automorphism. The simple Lie algebras of type G2 are the Lie algebras of derivations of octonions. By the way, there are no simple Lie algebra of type G2 in characteristic 3, so I will forget about this case. Anyway, it is relatively easy to classify gradients on the octonions. And fine gradients appear in just two ways: either the analogous to Cartan gradient, which is the eigenspace decomposition relative to a maximal torus, or octonions can be constructed using the Cayley-Dickson doubling process, starting with the ground field if the characteristic is different from 2. If the characteristic is 2, one starts with a quadratic field extension. But anyway, one can use this Cayley-Dickson doubling process starting with the field, and this gives gradients by two elementary groups. And essentially, these are all gradients on the octonions. And once we have the gradients on the octonions, we have this isomorphism, we can transfer to gradients on the simple Lie algebras of type G2. And that's all. And for instance, whenever one considers the gradient on G2, on the simple Lie algebra of type G2, the 14-dimensional simple Lie algebra of type G2, endowed with the gradient that comes from this gradient on the octonion, one gets a very nice gradient. One gets a gradient where the neutral homogeneous component is trivial, and then we have 7 other homogeneous components, and all of them are Cartan subalgebras. So we have a splitting of the simple Lie algebra of type G2 as a direct sum of 7 Cartan subalgebras of G2, and these are very nice gradients on these algebras. For F4, well, we can do the same, but with the Albert algebra, which is the exceptional Jordan algebra. And then we have the same situation. Assume that the field is algebraically closed, characteristic different from 2, and then we start with the simple Lie algebra of type F4. The group scheme of automorphisms is isomorphic to the group scheme of automorphisms of the Albert algebra, the algebra of 3 by 3 Hermitian matrices over the octonions. And then again, it's easier to deal with gradients on this Albert algebra, although historically this was not done so in this way. At least over the complex numbers, gradients were classified first in the Lie algebra setting over the complex numbers, and then moved to the Albert algebra. But it's easier to deal with this algebra, which is an algebra of dimension 27. And essentially, there are, if we restrict to fine gradients, only 4 fine gradients on this Albert algebra. And one is the Cartan gradient, the eigenspace decomposition relative to a maximal torus. And the others mix gradient by the integers and gradients on the octonions, or gradient on the octonions together with a Z2 square gradient, natural gradients of 3 by 3 Hermitian matrices. Or we can think of the Albert algebra as constructed not with octonions, but with another class of composition algebras, the so-called Okubo algebras. And Okubo algebras have a natural fine gradient by 2 copies of the integers modulo 3. And then using a cyclic symmetry of these 3 copies of the Okubo algebra, one gets another copy of the integers modulo 3 and gets a very nice fine gradient of the Albert algebra where all the homogeneous components have dimension 1. And this means that we can express the Albert algebra as a kind of twisted group algebra over this group. And again, if we move to the simple Lie algebra of type F4, which has dimension 52, for instance, this grading gives a very nice grading where, again, the neutral homogeneous component is trivial and all the other homogeneous components are two-dimensional, and we can put them together, each one with a corresponding to the opposite element, and then we again got a splitting of F4 as a direct sum of Cartan's values. So these are very nice games. But for the E series, we know about the over the complex numbers using other kind of tools, and including moving to compact Lie groups and studying certain subgroups of the compact Lie groups. And with this, we know what the fine gradings look like over algebraically closed fields in characteristic 0. An interesting thing is that in each case, there are exactly 17 fine gradings. Some of them come in families. So the same construction gives a fine grading for E6, E7, and E8. But some of them are completely different from E6 or for E7 or for E8. And even so, the number of fine gradings is the same and there is no clear regularity. But we don't know exactly how to deal with the E series in the modular case or even in the real case. And we don't know how to classify gradings even over the complex numbers, general gradings, not just fine gradings, up to isomorphism. So these are things that are open and we have no clear ideas of how to proceed. And well, over algebraically closed fields, most of what I've told you about appears in this monograph. But then if one wants to study other fields for, and even some questions about reality do not appear here, but have appeared in later papers. And this is the last paper together with Misha and Adrián Rodrigo Escudero, where we are dealing with real force of the classical simple Lie algebras. And even over the real field, things become more involved. And this is, it's almost 80 pages paper with a lot of technicalities, but some of the ideas are even perhaps in a nicer way here than in the monograph, if you are interested in some of the ideas that I've told you about. And that's all. Thank you very much for your attention.
Thank you, Alberto. Questions, comments? You can use also the chat.
So may I ask a question? So
yes, please.
So what is so you didn't, or you mentioned there was a question by Philip before, so, but what is known about Kac-Moody setup? So
we haven't studied the Kac-Moody algebras. What happens is that in order to define, or the natural way to define, let's say, a fine Kac-Moody algebras, one uses gradings on finite dimensional simple Lie algebras. But not much is known about general gradings on infinite dimensional Lie algebras. We still have problems, are fighting with the finite dimensional cases. So, yes. Although there are results about infinite dimensional associative algebras with some infinite dimensional associative algebras with some finiteness conditions, and some of these gradings can be transferred to gradings on Lie algebra. So there are isolated results here and there on some classes of algebras, but not the general way of attacking things, I guess. Yes, Seidon has raised his hand.
Okay, so Seidon, yes.
Yes, thank you. Thank you very much for the talk. I had a question. So you said that for G2, of course, you have the octonions, and for F4, you have the Albert algebra. I imagine there are structurable algebras that go in for E6 and E7. But my question is there a low-dimensional algebraic structure that plays a role in these 17 phi gradings on E8?
Yeah, well, what happens with structurable algebras and E6 is that there is a nice simple structurable algebra whose automorphism group is E6, but the simply connected E6. While in order to classify gradings on the simple algebra of type E6, we need the adjoint group. And then the diagonal subgroup schemes are not the same at all. So we cannot transfer. So we can use structurable algebras to transfer some gradings that we know and try to get a tentative list of all the possibilities that appear there, but not to classify. And yes, about E8, yes, we want to understand, well, we have constructions of all the fine grains. And so the classification of fine gradings relies on some results on compact Lie groups. And using these results on compact real Lie groups, we can move to complex, and from complex to arbitrary algebraic closed fields of characteristic zero. And so this has told us all the possibilities, and then we have been able to describe all these possibilities in terms of some nice constructions of E8. For instance, constructions using octonions or Okubo algebras, or structurable algebras, or some other systems. But again, okay, we can classify gradients on these smaller systems, and this gives a list, but to be able to prove that the list is complete. So most of the gradients not necessarily fine that we know come from constructions of certain types using small objects, smaller objects like composition algebras, Albert algebras, structurable algebras, and all this. But we don't know how to check that we have got all the possibilities, how to get a real classification. We don't know.
I see. Thank you.
Yes.
Other questions?
If I consider grading,
Please, yes.
if I consider grading of polynomials, what kind of knowledge I can get about polynomials?
Gradients on polynomials?
Yes, because product of polynomials at their power, so it's also grading algebra. So I can consider such some kind of property of this algebra using grading.
Yeah, I guess so. I mean, each time you have a gradient of certain type, this explains some symmetries of the algebras that are important. And yeah, and for instance, if you have an algebra and you want to determine the Lie algebra of derivations of this algebra, if you have a gradient that splits this algebra into small components, then you can compute the derivations, just homogeneous derivations, and this is much easier because you have to compute things in smaller vector spaces. So you get some extra restrictions that help us to solve the linear equations that appear there. But well, I haven't used gradients on polynomial algebras in all these things. So
this is another area.
Apart from the natural gradients on the polynomials, I don't know.
It seems to be a bit quite far off. Yeah. Other questions more related to the topic, please? Yeah. No, okay. So
when you were talking about the E8,
right.
were you talking about the complex case or the case of prime characteristics? So I'm not. I just want to understand whether you have a complete classification, say, over the complex numbers for E8.
Oh, yes, for E8 we have the classification of fine gradings over the complex numbers, or algebraically closed fields of characteristic zero. That's all we have. Fine gradients or in characteristic zero algebraically closed. Yes.
Thank you.
So for E8, E7, E6. For some forms, real forms of E6, we have some partial classifications. But only fine gradients and only in characteristic zero and algebraically closed. Yes.
Okay.
But the techniques for this classification are different from the ones I've told you, because we have not been able to transfer the problem to nicer or easier setting.
Okay, so I suggest to thank Alberto again. Okay.